Alrighty, welcome to kind of a mini lesson here on how to solve when we're dealing with exponentials and logarithms. So for these examples, we'll either be using a logarithm to get to our final answer, or we'll start with a logarithm and see how we can actually solve that out. So when I do this, I prefer to start with the exponentials because we have to use a logarithm to solve it. So as we get through this, we're going to see kind of all the different types of equations we could see. So we're going to start with this method. And this one is set up for when we have one exponential expression. So we can see here inside of our example, we have 2 to the x minus 1. That is our exponential expression. So here are the methods we're going to follow, or the steps we're going to follow. And for those of you who are already in my class, you have seen this when we were solving for intercepts in the last unit. We were doing this, you just didn't realize you were solving. So the first thing we want to do is we want to actually isolate the exponential. And we have that exponential here. So we want to get rid of everything that is not the 2 to the x minus 1. Once we do that, we're going to put it into logarithmic form. We can't do this until it is isolated. And then we're actually ready to solve for the variable. So that x is stuck up here in the exponent. We have to use this logarithmic form to get it out. So let's see what that is going to look like. So the first thing we're going to do is we're going to isolate. So I like to use the acronym SADMEP to help me isolate. See backwards order of operations. So I'd like to see first, is there anything I could add or subtract to the other side? And I see that I have a plus 5. Now that I've seen there's anything I can add or subtract, I go to division and multiplication. I can see I can divide both sides by 6. And we're here. Now, if you've been following my exponential, we've gotten to the point where the exponential itself is isolated. Now that it's isolated, we're ready to move on to step 2, which is to go ahead and convert it into that logarithmic form. So we know that when we're converting to logarithmic form, the first thing we're going to do is actually write the word log. We're then going to take the base. What was the answer becomes the argument. And what was the argument, or sorry, what was the exponent becomes the answer. So we've converted this into logarithmic form. Log base 2 of 3 equals x minus 1. We're now ready for the very last step, which is actually just to solve for the variable itself. To get x by itself, I know that I need to add 1 to both sides. So we get x equals log base 2 of 3 plus 1. And that's actually going to be my final answer here. Some of you guys might be saying, but that's not a number. That's okay. As a reminder, if you had your calculator here and you were actually trying to get a number, which when we're in the world of applications and how do we see this in the real world, we do typically want to get an actual number. As a reminder, you could do the log of 3 over the log of 2 plus 1. So you could use that change of base formula to turn this logarithm into these logarithms, and that you could put into your calculator. But I don't actually have my calculator here, so we're going to go ahead and move on. So you can see our steps: isolate that exponential, convert it into logarithmic form, and then just isolate the variable you're solving for. So this method, once again, you can see we still have an exponential. I just put this up here that we use this method when we have more than one exponential. So oftentimes you'll see like 4 to the 2x equals 32 to the 8x plus 5. And I could have done that one because we would have actually had an exponential on both sides, but this was the problem I had, so I just went with it. But we're going to see how we can actually rewrite 1 over 32 to be an exponential. But either way, if you have an exponential on both sides, or if you have numbers that you know have this can be rewritten with the same base, that is what this method is for. So looking at this, our first step here is actually going to be rewrite the equation to make the base the same on each side. So that's really the key part that we're looking at here. So here, I want to try and get 4 and 32 to have the same base. Now, my first gut instinct is, can I make can I rewrite 32 as a base 4? So I come over here and just double check. 4 to the first is 4. 4 squared is 16. 4 cubed is 64. Unfortunately, none of those are 32, so I'm going to try something else. I know that I can rewrite 4 as 2 squared. So I wonder, can I rewrite 32 as 2 to the something? And using my math knowledge, I know that I can say 2 to the 5th is equal to 32. So that's what I'm going to do here is I'm going to rewrite 4 as 2 squared. And I'm going to rewrite 32 as 2 to the 5th. So we've now rewritten them to make the base the same. Before we can get to part 2, there should actually be a little sub-step there that says go ahead and use your properties of exponents to simplify both sides. So here are my properties of exponents. I know that if I'm raising a power to a power, we're going to multiply there. So these can be rewritten as 2 to the 4x. And on this side, I know that because this is in the denominator, that means this one is actually negative. So I'm going to rewrite this as 2 to the negative 5. Now we've really completed step 1. Step 2 says to use this thing known as the one-to-one property. What the one-to-one property says is that if you have on either side of the equal sign, like we do here, bases that are the same, then the one-to-one means that their exponents must also be the same. If their bases are the same, their exponents must also be the same. So we can actually just go ahead and say 4x equals negative 5. Now that we've done the one-to-one property, we're ready to go ahead and solve for the variable. To get rid of the 4, I'm just going to divide it to the other side, and I get x equals negative 5/4. And there you have it. So this is a really, really useful one. Like I said, if you have an exponential on both sides, this is your go-to. It's also for ones that are really easy, or if you recognize the bases are really similar. So, 3 to the 4x equals 27 to the 9. That's a really big number, but I know that 3 and 27 share a base of 3, so you could rewrite this side. So if you ever noticed immediately that you can rewrite the base, go ahead and try this method. So starting here, if we go back a slide, this one I had an exponential, and so I had to use a logarithm to solve it. This one we had an exponential, and we kind of found a shortcut. We said we could actually rewrite the base, so we didn't need a logarithm. The next ones are going to look at what does it look like if we start with a logarithm? How can we go ahead and solve these? So I'm going to do, they're going to be similar. Follow this. It's going to be very similar. So we're back to the blue. So we're back to having only one logarithm. Well, once again, if you've been in our class and you've been doing the graphing, you've actually already done this and just didn't know it. What we've been doing is isolating the logarithm. So that's what we have right here, step 1. Isolate the logarithm, so that includes the word log, the base, and the argument. Once you've done that, very similar to our first example, now we're going to convert it into exponential form. And then last but not least, we're ready to solve for that variable. So let's see what that looks like with this example. So I'm going to highlight my logarithm again here. Notice that we're dealing with the natural log. So instead of the word log, it's going to be the ln. There isn't a base because the base is e, and the argument. Now we're going to get rid of everything that is not highlighted. So the first thing I'm going to see is adding that 8 to both sides. Now divide and multiply. I'm going to get rid of the 2. So I've done step 1. I've isolated the logarithm. So the only thing on this side of the equation, you've been following it, is the logarithm. So the ln of x minus 1. Now that I've done that, I'm ready to convert it into exponential form. I do have to use some background knowledge here, and the idea that the ln is the natural log, so the base here is actually e. So what I'm going to start with is e. 3 represents the exponent, and the argument represents the answer. Very, very last step then is going to be to solve for the variable. So I know I can just add that 1 to the other side. And there you have it. So oftentimes, if your answer involves E, we actually just leave it in terms of E. This would be your final answer. Once again, when we get into applications and you need to know what this number represents, then you could use your calculator here to evaluate. But typically, when we're just doing the basic algebra solving, we'll actually leave our answers in terms of E because it's more precise. So you can see hopefully the parallelism of this one to the very first example of isolating, converting, and then solving for the variable, isolating, converting, solving for the variable. But what happens if we have more than one logarithm? This one's a very, very similar idea. See, I call it method 1.5. We use this method when there are logs and just on one side. So still, I only have logarithms on one side, but I do have more than one logarithm. It's the same steps: isolate the logarithm, convert to exponential form, solve for the variable, but there's this extra step added before it, which is first to condense it down to one logarithm. Once you have it down to one logarithm, then you can convert it to exponential form, then you can solve for the variable. So here, the first thing I need to do is I need to say, are there any properties of logarithms that I can use to condense log 2x minus log of 5? Well, the good news is they do have the same base. Because nothing is written there, we know they're common logs, they're base 10. So since they have the same base and they're being subtracting, I'm going, hey, that's the division or the quotient property. So I can actually call this the log of 2x over 5. So we're using that division property there. So now I've condensed it, I only have one logarithm. Step 2 says isolate it. Well, luckily enough, I've actually already isolated. There isn't anything else I need to do here. Step 3 then says go ahead and convert it into that exponential form. Once again, using a little bit of prior knowledge here, I know that for the common log, the base is 10. So this is 10 to the first power equals 2x over 5. The last thing I'm going to do here then is to solve for the variable. This one is going to take a little bit more. When we solve, you have to actually do this operation out. So 10 to the first is 10. And now we can use that idea of SADMAP, but before we can do that, this is where some students get a little confused. So it starts with add or subtract, which would be a little bit more confusing. Say I had a +1 here. That's where students get really confused. But the biggest idea here is that in order to use the SADMAP, we have to have everything on the same level. You have to get rid of your denominator first. That is always, always, always the first step, is getting rid of this denominator. So we're going to bring the denominator up. That gives me 50 equals 2x. So x equals 25. Now, before I green light this, just so I'm going to highlight my green, I'm not actually ready yet. What I didn't write over here, which needs to be added to each of the solving log slide, is check your domain. And what I mean by that is we said the argument has to be positive. So anywhere you have an x in an argument, just go back and double check. If you plug your x in, it's still a positive number. So here, 2 times 25 gives me 50. That's a positive number, so I am actually ready to go ahead and green light this. We're good. It's ready to go. Say that I plugged that in and got negative 50, or I'd gotten 0, then we would have said that's an extraneous solution. So these two are very similar. They involve isolating the logarithm and converting it into exponential form. So you have to convert. But if we think back to the exponential one more time, for this one, we said, hey, there's actually some examples where we don't have to convert into logarithmic form. But when we get into solving logs, there's some examples that we don't have to convert into exponential form. So let's look at this one last example. So this one is when you have more than one logarithm, and the big thing here is, once again, they have the same base. So that's a really important part. If you aren't converting, that means you have the same base on both sides of the equation. So here, notice that I have 4, 4, 4, and 4. So because I have them on both sides of the equation, I want to be able to use that one-to-one property again. So the very first step we're going to do here is we're actually going to condense both sides. Pull my condensing color back out. Here, because they're being added, we know that's multiplication. So this becomes the log base 4 of 2x times 3 equals, again, this side they're being subtracted, so the log base 4 of 36 divided by 2. And go ahead and do those operations out. That gives me log base 4 of 6x equals the log base 4 of 18. So now we've done step 1. We've condensed each side to have a logarithm with the same base. So here they both have that base of 4. That one-to-one property again says if they have the same base, their exponent must be the same. But if we think critically, we know that in the world of logarithms, the exponent is really represented by the argument. So that means their argument must be the same. So since the bases are the same, their arguments are the same, so we can say 6x equals 18. Very last step, go ahead and solve. Once again, before I greenlight it, before I'm definitely sure, plug it back in. This is the only place with an x, so 2 times 3 is 6. That's a positive number. We are good to go. So there you have it. These are the most common examples of how you are going to be able to solve with or without, or with a logarithm or getting rid of a logarithm. So if they have the same base on both sides, so if you got things on both sides, same base, try to use this one-to-one property. If you just have logs on one side of it, get it down to one logarithm, so both of these are involved getting the logarithm by itself, and then convert. Similar here, if you got it on both sides, get them down to the same base, use that one-to-one property. If you can't, isolate it, put it into logarithmic form.